Okay, so folks, I'm sharing my screen now through a very useful book for all of us. Yeah, the book is called Introduction to Econometrics with R, and you can find it with this link www.econometrics-with-r.org. So it's a good book with examples and everything that you have here, and now you would have learned that there are actually quite a few things that we've covered from here. So we are basically somewhere here in this book now. Right, so we're here. Right, least square assumptions, etc., right? Okay, estimating coefficients, okay, right. So now, the least square assumptions is something that gets talked a lot about, right? And why are they important? Okay, first, the assumption that the error term has a conditional mean of 0, right? What do you mean conditional mean of 0? Can somebody explain to me what that would mean? In the example of our children and their weights, so the average weight of a 3-year-old is 5 kilos, and if you have 10 3-year-olds in the sample, right, then each child, so not every 3-year-old will weigh 7 kilos, right? Some 3-year-olds will weigh less than 7 kilos, some 3-year-olds will weigh more than 7 kilos. But if you average the weights of all 3-year-olds, the average will be 0. The deviations, right? So if you take the deviation of each 3-year-old minus the average weight of all 3-year-olds, and if you average all these deviations, because deviations from the mean, they'll be equal to 0. But why is it conditional? Because it's conditional on choosing only 3-year-olds. You can't say that that's true for all the error terms, right? So once you fix the age, when you fix x is equal to 3, and then take the error terms from that, and if you average those error terms out, their average will be 0, right? That's what's called a conditional average. Sure? Okay. All right. So, we have this. Now, okay, now you see that that's true only if the model is correctly specified. For example, the model is y is equal to a plus bx. Suppose the actual relation is not linear but curvilinear. Suppose a quadratic equation, right? But it's misspecified as a linear regression. Then you might not get the property, and that's what we are going to see now, right? Okay, so first do this in your RStudio, right? Set.seed 321, because we're going to generate some random numbers. We want all of us to generate the same random numbers, right? With a random number generator, everybody will generate different random numbers, no? So we should all submit the same random numbers, no? One country, one language, one set of random numbers. You have to generate 321. Right? That will set seed. So basically, some number which you put there will give you the same, we kind of generate the same random numbers everywhere. right? X equal to R unif will generate 50 random numbers from the uniform distribution, where each number has the same probability of occurrence, right? Minimum -5, maximum +5. I think somebody is trying to join. Yeah, so this will generate random numbers, 50 random numbers from the normal distribution, that's the error term. And so suppose the actual regression is y is equal to x square plus 2x plus u. So it's not a linear regression, right? But we fit a simple model where we regress y on x. Right, so we get the functional form wrong. Okay, and then see what happens. Whereas a quadratic model is actually y regressed on x plus x square. You put I into bracket x square, because otherwise if you just write x plus x square, the computer will not know whether that x plus x square are two different variables. It will just think x plus x square is one variable. Computationally x is one variable, x square is another variable. And for that you put it into an I. Right? So we'll run two regressions and then see. So what happens if you get the functional form wrong? Right? Okay. And then we'll do the predictions. Right? So calculating y hats, all of you would have known that, right? So you put the values of x in the model, you'll get values of y. Those are called the predicted values of y. Right? So let's do that. Shri Acharya will admit this lady. Done this? I meaning, see, we are regressing y on x and x square. So in general, in R, if you're doing a regression and x and z are two independent variables, say y is equal to lm y tilde x plus z. Okay, but when you're doing x plus x square, computer needs to know that x and x square are two different variables. You don't add x and z together, x and then x square and them together and put them as a single variable. So if you put I, then it knows that x is one variable, x square is another variable. Though in general that's not really strictly necessary in modern, but still do it, safer. R is smart enough actually, but theek hai. It's only actually if you put x plus x square in a bracket that it would think of them as one variable, but safe is this side. So a quadratic model and a linear model. Okay? We were here, right? And then you have to plot the results. Yeah? So red line will be the So basically you have to produce this graph, plot. Let me kind of bring it here, make it a little bigger for you guys to see. Become a little bigger? Yeah? I mean, you can just copy paste this and put it into your. So if you open this on your computer, just copy paste and put it into R, right? It'll just work. You don't have to retype everything again. So I've been able to produce this picture? Okay, now understand this, right? The regression line is the conditional mean line. So you find the conditional mean of y for a fixed value of x. Then you take the value of x, put a perpendicular here and put a perpendicular on the y-axis, give the conditional mean, right? The points around, you see the data are scattered around the points, right? The deviations are the gap between this point and this line, right? So if you average, if you look at the deviations around the red line, they're all plus and minus, correct? They'll cancel each other out, they'll average out. But if you look at the deviations around the blue line now, then the errors are all positive and large here, the errors are all negative and large here, errors are again positive and large here. So there is no guarantee that they would cancel out, right? If you look at the errors around the red line, then some of them are below, some of them are above, and there doesn't seem to be any systematic pattern around the red line. Yeah? The scatter on the red line, it's clear that there is no systematic pattern in that. Whereas for the blue line, you see a systematic pattern in the deviations, right? Okay? Up to the point where the red line is above the blue line, all the errors are positive. Because the blue line really is a mistake. The actual relationship is curvilinear. We are trying to put it in a straight line, right? So the expected value of errors is not 0. That's because we have misspecified the functional form. Yeah? Right? So it's very important to get the functional form right in the first place. Correct? Yeah? Okay. Okay. Now the second assumption is that all the data are identically and independently distributed. Right? So what is the idea? You want to test the relationship between income of a household and their expenditure on education in Pune. So EXP is your expenditure, Y is your income, right? And you collect data on a sample of say 1000 households. The idea is that, and some of these households might you have chosen them randomly. So some of these households are in Ghorpadi, some of these households are in Khadki, some of these households are in Deccan, some of these households are in Pashan and so on, right? The underlying assumption are two. That A, your data are independently distributed, right? So one particular household that you've got has nothing to do with what other households around it are doing. Sure? Okay? Right? There's a man called Thorstein Veblen who would have got very angry with this assumption. You heard of this man, Thorstein Veblen? What did he say? What did he say? Do you remember what Thorstein Veblen said? He said, we like to do as our neighbors do, no? We like to do better than the Jonases. So if all your neighbors are sending their kids to expensive schools, you'll also want to send them to expensive schools. Right? Okay? It will be a shame, no? If all your kids, all people in your building are going to some IB schools and you go to some Jilla Parishad school. Right? You feel very sad. Though of course, no reason one should not go to Jilla Parishad schools. But so there are those effects. Right? So data might not be independently distributed. Right? Okay? But the assumption is that there are no Veblen type of people here. Right? Okay. And that's a problem. Okay. And secondly, the other assumption is that the data are all identically distributed. So the relationship, the distribution of the data between, say, income, so the data are coming from the same distribution, whether the household is picked from Pashan or in Ghorpadi or from Deccan. Right? Sure, and the relationship is the same. Now, many times on spatial data, that doesn't work really. Because the relationship between income and expenditure by the data you're picking up from a slum population might be a different population compared to, say, somewhere else. Right? Okay, so those are non-homogeneous populations. And for that, linear regression models don't work. You have to do other things which are geographically weighted regressions, or some ideas from things like for example, economists now using a lot of techniques from image processing and image recognition, right? So because image recognition, you need to recognize a face, no? The same face everywhere. So what the data on that face are different from the data on the neighboring face, right? So you need to, right? So that those kinds of things are there. But usually the assumption here is that, so that's a strong assumption that we are making, right? One is there are no Veblen kind of effects and the homogeneous is the same, and that's a problematic assumption. But nevertheless, so basically, so for example, for time series data, this might not be assumption. I mean, it's generally said that the assumption is not true, right? Data are not independent. So what happened last year matters a lot for what happened this year, right? The economy had COVID last year, then the COVID effects will kind of spill over into the economy. So for time series data, especially, they are not, right? So this is just an example of how to generate time series data, right? So we're looking at employment at time period T is some number minus 50 plus 0.98 into employment in the previous period plus a random error term UT. Right? Sure? So you can generate this data. Right? You can artificially generate this data and see how it looks like. So time series data, this assumption is not valid. Because the state of the economy today depends upon the state of the economy last year and the year before the last and so on. Alright? This is called, yeah, so Doing this? Yeah? And then you have to plot these results. Hey. I'm so sorry, this goes very fast. Yes, you plot the results. On the x-axis you have time, on the y-axis you have x. Type is equal to L means type is line. Color, whatever color you want to choose, right? And you see that there is data where you can see clear dependence upon time, no? The data declining in time. Had there been random data, then that data would have, there would be no trend in the data. Right? Sure? So that's an example of data where, okay, the third assumption is large outliers are unlikely. Right? So for example here, so take an example. Okay, what happens if there are just some numbers, just one or two variables, one or two data points, right, which don't fit the data. Right? If you include them and you exclude them, look at what happens to the regression. Right? So we're going to do two regressions. One is, we're going to generate the data again as you now know how, so just 10 data points, except at the 9th point of y, we are going to set up to a very high value of 2000. So x is basically random numbers, uniform distribution from 30 to 70. Right? Y is random numbers 10, mean 200, standard deviation 50. And the 9th value of y we are fitting to 2000 artificially. Right? And then fit y on x. Right? And then you fit a model without outlier. This is called an outlier because it's a large value. Yeah? And you fit a model without outlier, we say LMY minus 9 and x minus 9 to use x and y without the 9th observation. Okay? And then plot the two results. So fit them. Done? So sometimes outliers can really matter. केलं? झालं? Done? Yeah? Savita, झालं? Okay. And now plot the results. See what you see. So if you run this, you'll get a model with outlier. You'll see they are completely different regressions just because of one observation. Yeah? Fortunately, R has all the diagnostic boxes to kind of deal with that. What do you see here? Model with outlier is a positively sloped model, right? But if you remove the outliers, why is that happening? Because there is just one big outlier here, which is biasing everything like this. Yeah? Right? Whereas if you remove the outliers, actually a negative downward sloping relationship. So one must learn, so one must be very careful to think of functional forms in the data, whether it's a quadratic relationship first. So the first key really is to eyeball the data. See the data. Right? See how things look like. Have a good understanding of your data. Try to see if there are some outliers somewhere. Right? Okay? Sure? Okay. Right. Okay, now there are some things we need not really. Okay. Now, suppose we have done a regression. Okay? And what is the expected value of beta? It is the population value of beta. Expected value of beta is the population value of beta, the law of large numbers, right? So expectation beta hat is an estimator. So it's a random variable. Beta hat will be different from sample to sample. Beta is the true value. And unbiased test would require expectation beta hat to be equal to beta. Right? Now I'm going to go into a lot of derivations here. Right? Okay. Okay, so basically, just don't worry so much about this as of now. Variance of beta hat, which we said, is actually equal to the variance of the error term divided by n upon the variance of x, right? Okay, but at the moment, don't worry too much about this. Okay, so look at this simulation below. What does the simulation do? It generates random samples of xi, y of 200 observations, where basically the regression equation is y is equal to 100 plus 3x. Right? Okay, so what it does is estimates a simple regression model, stores the estimate slope beta 1 and visualizes the distribution of beta at 1 as observed so far using a histogram. Right? Okay. So basically, as I keep on increasing, right, so this is the data point getting generated, this is the distribution, right? So you can see generally centered around 3. Yeah, so that's the. And we have done these simulations, so I will not bother you with these simulations again. Yeah? Okay, let's come to hypothesis testing straight away. SLR means simple linear regression model. Okay, so install these two libraries. Okay, so you need two libraries. AER is a book called Applied Econometrics with R and a library called Scales. AER is a very famous book, Applied Econometrics with R, book by Kleiber and Zeilis, which came out in 2008 or so. Right? That's where all of us really learned econometrics and R could be done together and all. Okay, now we need to test hypothesis about the, right? So basically the t-test is, the null hypothesis is whatever the hypothesized value, right? Whatever the hypothesized value, estimated value minus the hypothesized value upon the standard. Just like a t-test, no? X bar minus mu upon standard deviation of x, right? Where mu is the hypothesized value. So just like that, the estimated value of beta hat minus the hypothetical value of beta hat upon the standard deviation of beta hat, which is the standard error of beta, just like the usual t, right? Sure? Okay. Okay, so the formula for the standard error of beta hat, I'm not going to go too much into that, right? How it can be derived? It can be derived very easily. Okay? Sure? Under assumption of no autocorrelation, that just becomes sigma square upon n upon etc. But we need not bother about that. The general formula. Right, if you have y and x, the general formula is for sigma square beta 1 upon n into 1 upon n minus 2 xi minus x bar square u hat I square upon 1 upon n summation xi minus x bar square, etc. Right? Okay, and then you get beta 1 hat minus beta 1 0 upon standard error of beta hat 1. Right? So basically take a usual t-test, right? Yeah. So for this CA schools data set, we need to find the relevant library. I'll tell you what library you need to have for the CAS schools data set. It's in AER only. So you have to look at the data. First tell me what the data set is. Right? First look at what the data set is and tell me what the data set is, CA schools. What you want to do is the average test score of students is dependent upon the teacher-student ratio, student-teacher ratio, right? Okay? So higher the student-teacher ratio, you would expect lower the scores, right? Sure? So basically CS, so what does this do? This creates a variable $str, which is the student-teacher ratio, which is the students divided by teachers. Yeah? So CS schools $students takes the data on students from the CS schools data set, divides it by CS school $teachers. Yeah? And so you can create an average score, so reading score plus math score upon 2. Yeah? Okay. Wait. And you estimate the linear model and then tell me what is the relationship. What do you think is the relationship? What do you think is a relationship? Negative? But can you first do a GG plot and see whether there are any outliers or so? Is the relationship linear, non-linear? So first do a GG plot. You know how to do a GG plot? X-axis, student-teacher ratio. Y-axis, average score, right? And then do geom understroke point, right? See how the scatter looks like. And tell me what you can learn from the scatter. And then we'll ask, so is there any sudden outlier? Is the relationship linear, non-linear? Because you can expect a non-linear relationship, no? Why? Because if the student-teacher ratio goes at 100, then there will be a very poor academic score, right? If it becomes 200, that score might not drop that much because, beyond 100, having more students doesn't make any difference because anyway there is no learning, right? So it could be a relationship which is like this, which becomes much steeper at the, which doesn't stop mattering, right? So is it a relationship like this? I don't know. My laptop has gone for a toss, so I'm using Savita's. It stopped charging. So what do you see? Somewhat downward slope. They're really scattered, right? Okay. So now run a regression. Once you do an LM model, what are the coefficients that you get? Linear model?
Intercept is 698.9.
Right.
And slope is minus 3.2.
Yeah. So you will get this regression? Yeah? And if you say summary of the model, see what you get. What you get is the R square.
.05.
0.051. So what does it mean? Only 5% of the variation in the test score is explained by the student-teacher ratio. Right? Okay? Pakka? Okay. Then we now have to test whether, now this is 2.28 that you've got. You want to test whether that is a statistically significant number, because there doesn't seem to be a very strong relationship between student-teacher ratio and the test scores. There's a negative number, but if you took another sample, you might get another number. What you want to see is the average value. So let's hypothesize that the true value of that coefficient is 0. So construct a test statistic with the estimated value minus the hypothetical value upon the standard error. Right? Okay? And which so if you look at the summary linear model, you get the t value there, you get the standard error, you get the t value. If you do the LM, you will get a t value, right? What is the t value that you get? No, t value 73 point, that's for the intercept, right? For the STR coefficient, for this minus 4.75, right? And so the null, so if you get the p value of 0.000278, right? What does that mean? That yes, the null hypothesis that this coefficient is statistically 0 can be rejected, and if you reject it, the probability of type 1 error is 0.00, so probability of going wrong is only 0.000278, etc. Right? So there is a strong relation, there is a strong evidence, there is evidence that that student-teacher ratio matters, though not greatly. It is not everything, it doesn't determine everything, but it's important, statistically it's significant. Right? Even if the R square is small, if the regression doesn't really explain much, the student-teacher ratio is still an important, statistically significant determinant of the average test score. Right? Yeah. So basically this is what you get. If you look at the standard error in that regression, so if you do the regression, you get something called the standard error, right? So the standard error of STR is 0.4798. That's the standard deviation of the coefficient. Estimated standard deviation of the coefficient, right? Come down here, you get the null hypothesis, the hypothesis, the estimated value minus the hypothetical value divided by the standard error is approximately equal to minus 4.75, right? And the p value is pretty small. The degrees of freedom are n is the total number of observations, minus 1, n minus 1 it has to be, minus k, number of parameters that have been estimated. How many parameters are there in the regression model? 2. 2, constant and the intercept, right? So n minus k minus 1. So if you just want the degrees of freedom, you can say whatever model and $df dot residual, right? And if you want to know how that 0.0027 came up, then you have to take PT. So what is PT? Minus 0.4751,327. Probability that the t value, t distribution with 418 degrees of freedom takes a value less than minus 4 point something. PT bracket minus 4.751327, DF is equal to 418, will tell you the probability that a t distribution with 418 degrees of freedom takes a value less than minus 4.751327. Right? And you want to say it's a two-tailed test, no? You have to multiply it by 2. And that is the number which you get. right? So you got a t value, some t value, area to the left of this, area to the right of this. Area to the left of this is given by pt multiplied by 2. So as a result, you don't need the t table or anything like that. Our computers can tell you what those values are. Yeah? Okay, so now interesting, right? You want to draw this picture with those colors and everything? Yeah? Okay. So draw this now. Okay, it's a long drawing, but ठीक है. So standard normal distribution, like between minus 0.6, minus 6 and 6, and you want to kind of color that, right? So you want to area to the left of minus 1.96, area to the right of plus 1.96. You want to draw that area in a different color and all that, right? The energy has gone into really is doing that in the color, but ठीक है. So first generate the t distribution between minus 0.6 and others, right? So you create a sequence between minus 6 and plus 6 at every 0.01 thing, right? So minus 6, so basically 0.01, 0.02 like that, right? From minus 6 to plus 6. So first create a t sequence. This will help you to teach. If you can really draw those graphs like this, no? Good too. If you color those rejection regions, the students get attracted to them. Actually, students get attracted to anything that is colorful. What I have learned over the years. They're like bees. Done that? Did this? Okay. So now let's go down below. So this is the t value, right? This is the t value, the actual t value. Yeah? Then you create an axis. Okay? And then you shade the critical region. Right? You need a kind of a, by a command called a polygon, you shade that region. So you get a color for that region. Right? Clear? Done? Everybody's done this? Okay. Now the next critical region. Polygon. This is standard plot functions in R. Okay, this is not ggplot. Basic plot. Yeah? Then you can add arrows also. And you can add an expression. Okay, so text. So you get a picture like this. Are you getting this picture? Yeah? Right? So basically what this will tell you students is that okay, we are looking at a 5% critical value, right? 5% level of significance. This is half of it because we are using a two-tail test. Therefore it's 0.025 is alpha upon 2. So what is alpha here? 0.05. That is the level of significance. Alpha upon 2 is 0.025. So this is the left side region, this is the right side region. And where is our critical value lying? Here. Right? But we are going to reject it as a two-tail test. So even if it lies to the left or lies to the right, we are going to reject it. Right? So therefore it now shows the students where is the t value. Minus 4.75 plus 4.75. So from this picture it becomes very clear, right? How do you take a test of hypothesis? Right? And what it really means. Yeah? Okay. Okay, now these are regression coefficients. So they are basically what? They are estimated values, no? So suppose the estimated value of, say, suppose you're studying the relation between consumption expenditure and income. And if you find the coefficient of income is beta, consumption expenditure is the dependent variable, income is the independent variable. Beta is the standard deviation, beta is the coefficient of income on expenditure, right? So how much does expenditure increase if income increases by some amount? Now it's an estimated value, right? So you get a value of say 0.7, could also be 0.8 or it could also be 0.6. You need to be able to say that if I take say 1000 such random samples, then what are the two values, two limits under which my estimated values will lie with 95% probability or 99% probability. Because different samples get different values of beta, right? Sure? So you don't want to say that, for example, because I've got this estimate, the beta is 0.8. Beta could have been 0.6 or beta could have been 0.9. Right? So you want to be able to make a statement that look here, if you take a random sample and do this regression, then there is a 95% probability or 99% probability that the estimated value of beta will lie between these two intervals. These are called confidence intervals, right? So how to generate confidence intervals is here. So basic formula is if beta hat I is an estimated value And if you look at a 95% level, then 95% 1.96 minus 1.96 are the critical values for the standard normal. Right? Sure? So what you do is beta hat I minus 1.96 into the standard error of beta hat I plus 1.96 into the standard error of beta hat I. Right? If you want to make it a 99%, then that 1.96 will have to change to the appropriate value for the normal distribution, standard normal distribution. You have a small sample, then that will depend upon the t distribution. You have to find a 95% value for the t distribution for whatever degrees of freedom. Right? For a very large sample, we know that it doesn't matter. So this is about for large samples. But if a small sample, then that value will have to be taken from the t distribution. Right? So the estimated value plus. Hello?
Sorry, sir.
Yeah.
Can you repeat? Can you repeat?
Yeah. So the question that we are trying to ask is that even so the beta hat value that we get from a regression is an estimated value. It depends on the sample. If I take a different sample, I'll get a different value of beta. Right? I know that on an average the beta hat values will be equal to the true value of beta. Right? But I can ask a different question. I can say, okay, if I take say 1000 samples, I know that each sample you'll get a different value of beta hat, but can you tell me two limits within which at least 950 of your 1000 values will lie? Right, some 50 values outside these that's fine. I can give it to statistical chance because, right, then I'll be using a 95% confidence interval. Right, so the values of beta hat between 2 points with 95% probability is out of 1000 such random samples, 950 will lie between that. It's a very helpful thing, right, because it gives you what is the uncertainty. Right? Okay, so that is given by the estimated value minus 1.96 into the standard error and estimated value plus 1.96 into the standard error. Right? Okay, where standard error is the estimated standard deviation of that beta hat coefficient. Why minus 1.96, 1.96? Because we know that if the sample size is large, the distribution of beta hat is standard normal. But if the sample size is not large, so the correct value is given by the t distribution, then this minus 1.96 plus 1.96 will be the t distribution value with those degrees of freedom. Right? There will be some t distribution values also, so that 2.5% distribution lies to the left and 2.5% distribution lies to the right. For large samples, it doesn't matter whether you use the t distribution or the standard normal, like we saw in the class. But for small samples, it matters, so you'll have to choose it like this. Okay, another point. So this is the standard error of beta. What is standard error of beta hat I? The uncertainty in beta hat I, estimate of beta hat, right? We know that as the sample size increases, that uncertainty becomes smaller. So the confidence intervals will also become smaller with the sample size. Because beta hat plus 1.96 into standard error is small, it will become small. So the accuracy of the estimates will increase if the sample size increases. Right? We also learned in the last class that if you omit an important variable, which might not be correlated with an included variable, if you still omit it, then the variance of that variable also gets in the standard error, right? In the standard deviation of the error term. So if you omit variables, the standard confidence intervals will be large. If you don't omit variables, if your regression is perfect, then the standard errors will be small. Right? So the impact of omitting variables is to make the standard errors wide, create uncertainty. Yeah? Okay. So let's generate a y, right? Okay, and they plot the y, right? First generate a y. या ये प्लॉट किया, जस्ट कॉपी पेस्ट है ना. So assume that the data generated by yi is equal to mu plus ei. So the mean value of y is constant and there are error terms. So there is no x variable. Y is just the intercept. If y is just the intercept, it means that the mean value of y doesn't depend upon x. The mean value of y is constant. The conditional mean of y is independent of x. Right? Okay, but y values will keep on fluctuating around that mu. Right? Okay. So now, and we know that the error term is normal, mean 0, standard deviation 25, right? The way we have generated this, standard 5, so variance is 25. Yeah? Okay. So what is the estimate of mu hat? Sigma square E upon the square root of n. Yeah? Okay. Which is 5 upon square root of 100. So the confidence intervals are given by mu hat minus 1.96 into 5 upon root 100, mu hat plus 1.96 into 5 upon root 100. Yeah? Because sigma upon root n is the, we learned, no? If there is a sample, if x1, x2, xn is a random sample of size n, if you calculate x bar, then x bar is a random variable which has the same mean as the population mean, but the variance is the population variance divided by n. We learned that, right? So the standard deviation is nothing but the population standard deviation divided by the square root of n. Right? Sure? So basically instead of sigma beta hat, it becomes 5 upon root 100. 1.96 minus 1.96 because you got 100 data points. So you can use a standard normal 5% cutoff and you get an estimated value of mu hat. Right? So mu hat plus or minus. So you basically get this. Get upper and lower. So the 95% confidence interval for the estimate of mu is 4.50, lies between 4.50 and 6.46. So if you take 1,000 samples from this population and do a regression, in 950 of those samples, the value of mu hat will lie between 4.50 and 6.46. Yeah? Okay. You can draw this graph later on. Yeah? Okay, so basically they're all the ones, the red ones are the ones which are not falling in that confidence interval. They're not falling in line. Right? They're the badly behaved ones. Right? Yeah? So they're here. Once you understand what it is, okay. Now, we come to what are called dummy variables. Heard of dummy variables? So many times the x variable that you get is not a number, it's not a quantitative variable, it's a qualitative variable. Is it hot today? Yes or no? Right? It's a qualitative variable. What's the temperature today is a quantitative variable. Right? Okay? Sure? Okay. So right. So we basically, what we have is, for instance, in our example, we could want to distinguish schools which have a student-teacher ratio less than 20 and schools which have a student-teacher ratio greater than or equal to 20. Right? So we think of a variable di which takes the value 1 if the student teacher ratio is less than 20, and di takes the value 0 if the student teacher ratio is greater than 20. So we can think of good schools and bad schools, for example. So good schools are ones which have a student teacher ratio less than 20. Bad schools are ones which have student teacher ratio greater than 20. Right? Okay? Sure? So di is equal to 1 if the student teacher ratio is less than 20. But sometimes schools with really, I don't know whether that's really right. Because the school I went to when I was very small actually had one teacher teaching 2 classes. Right? And we used to sit in 2 classes. We used to go from one class to another. So when we went to one class, we used to all run away from the second class. At least I used to. And then come back before he came back to that class, right? And I learned so much outside the classroom compared to what I learned inside the classroom. Yeah, but so depends, right? So I school district less than 20, greater than 20, right? So you have, now understand what this is, okay? So test score is beta 0 plus beta 1 di plus mu I. So for good schools, what is di? Di is 1. So the model for good schools is beta 0 plus beta 1 plus mu I. What is beta 0 plus beta 1? The average test score. Right, when with the model yi is equal to mu plus ei. Mu was the mean, no? And then yi fluctuated around the mean. So instead of mu, you are going to have beta 0 plus beta 1. So beta 0 plus beta 1 is the mean for schools which have less than 20, which are good schools. And for bad schools, what will be the model? Beta naught. Right? So if you are testing the hypothesis whether test scores are better for schools which are good, then we would expect beta 0 plus beta 1. If you want beta 0 plus beta 1 to be greater than beta 0, then beta 1 better be greater than 0. Right? So our test of hypothesis could be whether beta 1 is greater than 0. It's a one-tailed test for beta 1. Yeah? Right? Sure, so look at carefully what I've done, what this guy's done. He said yi, so beta 0 refers to bad schools. And beta 0 plus beta 1 refers to good schools. Right? So what is the baseline case? Bad schools. And we are saying whether good schools do better relative to bad schools. So bad schools is the baseline category. Any category where di is equal to 0 is the baseline. And beta 1 that you are going to get will tell you whether good schools are doing better than bad schools. If beta 1 is negative, they are doing worse than bad schools. If beta 1 is equal to 0, it says there is no difference between the two. So beta 0 already stands for the reference category. Right? Now suppose we had kind of said like this. Think of 2 dummies. D1 takes the value for good schools and 0 for bad schools. And D2 takes the value 0 for good schools and 1 for bad schools. What would have been the problem? And suppose we had an intercept also. We are having too many categories, right? Because we would not have known what the intercept stands for. Here there is one dummy for the good schools. Bad schools is given by the intercept. If you have a dummy for the good schools and a dummy for the bad schools, then you would know what the intercept means. Econometrically, you would say the intercept is unidentified, or you have an under-identified model. You can't assign meanings to all the coefficients. Yeah? And the regression would say, I can't do it. You are into what is called the dummy variable trap. It would say either you run a model without an intercept or include an intercept If you're going to include intercept, remove one of the dummies, whichever ones you want to. Yeah? Whichever of the two things you want to do, you can do. Is this clear? So you should never have as many dummies as the number of categories you have if you're going to have an intercept in the model, because the intercept is already giving you the baseline category.
But in this case, good school and bad school are complements. I mean,
Yeah, so basically beta 0 would stand for the average performance of bad schools, and beta 1 would stand for the comparison. So beta 0 plus beta 1 would be the performance for the good schools. So beta 1 would be what the value added of the good schools is over and above the bad schools. So bad schools is the basic category.
So there is no intercept.
If you have an intercept, the intercept will automatically stand for the baseline category.
But then what intercept represents in a linear regression model?
In a linear regression model, the intercept merely represents the condition mean of y when x is 0. That's all, or at the beginning of the data.
so if we have another criteria as in
So if you have a dummy variable where yi,
to city or like that.
okay, so good school, so student teacher ratio is one category, right? And say maybe the school is a Jilla Parishad school or not, will be another category. So you have D1 and D2, right? So your model is yi is equal to beta 0 plus beta 1 D1 plus beta 2 D2, right? Sure? Okay. So what would beta 1 and beta 2 stand for, right? What would beta 1 stand for? So think of a model where you have a school which is a good school and a Jilla Parishad school. So the model will be beta 0 plus beta 1 plus beta 2. Right? Sure? So beta 0 is a school which is a bad school, not a Jilla Parishad school. And beta 0 plus beta 1 plus beta 2 will tell you the performance of a good Jilla Parishad school relative to a school which is neither a Jilla Parishad school nor a good school. Right? Whereas what would beta 0 plus beta 1 tell you? Good school which is not a Jilla Parishad school. Right? So therefore those coefficients have to be understood in a very in a proper way. Right? Yeah? When this rings, somebody is trying to come. Please join, please join. Hey, Chaturthi was there all the while. Yeah? Okay. So now do this. So test score is the model, right? So we are creating a dummy. Yeah? CS school $D, just take all CS schools $STR which are less than 20. We are just taking those schools where less than 20, right? So good schools. And you calculate the mean score for that. Conditional upon $D is equal to true, right? And then you create a mean score for $D is equal to false. So you need to go to Excel and create that, right? This will do it in its own. We have lots of dummies, no? Then it will become very difficult. Like all that mission until it I said, okay, what if a particular village belonged to Maharashtra, it should be 1, otherwise 0. Then you have 6,40,000 villages. So Excel will go 1, 0, 0, 0. And if I want to be particularly cruel, I'll mix up all this. You don't find a state variable, right? You have to check state. This can be done very quickly here. Yeah? Okay. So mean score, right? Chai? Okay. You want to do this while we take a small break? So basically what you get here is, this is the difference, right? The red dot is the mean score for schools which are good schools. The red dot on this side above 0 is the mean score for schools which are bad schools. And
Bad school and one is good school.
yeah, one is good schools, right? And the spread is the data. You can see that this dot is a little higher than this dot, right? It's basically you're comparing the two means really. When you're looking at the statistical difference of beta, you're basically doing what? You're only comparing whether this mean and this mean are statistically different. What you're taking is a t-test really. So the t-test which you get in the regression will be the same as the t-test which you would get if you have to compare the two means, right? Okay, so let's do this now. You can do this till we go and have a cup of tea. Once you do this, you can have a cup of tea. So did you manage to draw this? Ala? And what did you learn from that? So basically, so data are only two, right? There are only two groups. One is test scores of students who are in the bad schools, which correspond to di is equal to 0. So all the data spread over di is equal to 0 is the test scores of students who are into bad schools, right? Bad schools, I mean student-teacher ratio is less than, right? That's just a term that we're using, right? Whereas all the students are going to schools with student-teacher ratio greater than 20 are all 1, right? And the data there, the spread there is that of students of those test scores. And the red dots in both the cases show the mean values, right? So this is unlike a usual regression, right, where y is equal to a plus b, x would be a continuous variable, y would be a continuous variable, and then you would get a line joining, you would get a line of best fit and so on. Right, here you really can't talk of line of best fit. So if I did an r square in this, it won't really make much sense, right? Okay, because what am I doing? Really, I'm connecting this dot with this dot, right? Okay, so what you really have to do is to see whether this red dot and this red dot are statistically the same or they're different from each other. So what are you really going to check? You're going to check whether the mean value of schools which correspond to di is equal to 1 and the mean test scores of schools which are di is equal to 0, are those two test scores, are the means statistically significantly different, but which is just a t-test, a simple student's t-test, right? So if you did a regression, you would get the same result, so the same t value, right? If you get a regression, so basically if you did yi is equal to beta 0 plus beta 1 di plus ei, and if you did a t-test for beta 1, what is it? If beta 1 is not statistically significantly different from 0, then the means of two groups are the same. If beta 1 is statistically significantly different from 0, the means of the two groups are different. So testing for beta 1, statistical significance of beta 1 is the same as taking a simple t-test of comparing the two means, right? There is no difference in that, right? Yeah, so that's exactly what. So now run this model. And tell me whether good schools have better scores compared to bad schools.
P value is very small.
What does it, and what is the coefficient? Is the estimate of D true? So the estimate is 7.169 and the p value is very small. So you reject the null hypothesis that beta 1 is equal to 0. Beta 1 actually is higher than 0. What does that mean? That the mean test score for good schools is beta 0 plus beta 1. The mean test score for bad schools is beta 0. So the difference is beta 1, which is statistically significant and positive, which means that good schools have a higher test score compared to bad schools. The test score for bad schools is beta 0. The mean test score for good schools is beta 0 plus beta 1. So what is the difference between the two? Beta 1. And beta 1 is statistically significant and positive. That means that good schools have average score compared to bad schools, right? Okay, sure. Now, this allows me to do a little bit more testing, right? I'm going to go to another textbook. I'm sorry, I keep on shifting like this, but there's another book which is also free for you, right? So, this book is called Effect, right? This book is called Effect. The Effect. No, sorry, it's called just The Effect, okay? The Effect is a film. Effect book. Okay, Effect, Intellectual Research Design, which is also free. Okay, so now let me take you to, you can read the rest of it about how to do policy evaluation and so on, but let me kind of take you to what are called a difference in difference estimator. Okay, which uses the dummy variable. So let's kind of, okay. Hey,
Dummy variable, is it always true that it is a one-tail text?
no. You guys want to test whether it's bigger or lesser. So you can have a two-tailed test also. If you find that beta hat is negative, right?
So beta hat will depend on my dummy. I mean, if I
No,
shift
so
the
what is your null and what's your alternative? If your null hypothesis is that both are same, and the alternative is that the better schools have better scores, then you would expect beta 1 to be positive. To be a one-tail test. Whereas if your null hypothesis is the same and the alternative is that that's different, then it could be a two-tail test. If they're worse, then it could again be a one-tail test. Right? Okay. Now this is a very important, so basically you have a very interesting technique based on dummy variables, right? So suppose there is a hospital, right? Okay, suppose there is a region, right? Okay, which say does not have a hospital. Say in Gadchiroli, for example, right? Access to hospitals is, so you keep on hearing these stories, of women being carried into baskets for maternity and all that, and so there is a lot of maternal mortality, right? So what we do is we actually set up a hospital, say in Nandurbar, okay, yeah, and then what we do is basically after 5 years down the line we look at maternal mortality. And we find that maternal mortality after the hospital opened, 5 years after the hospital opened, is significantly lower compared to maternal mortality before the hospital opened. Right, so 5 years have passed, right? Maternal mortality is now lower, right? Okay, it used to be high now, earlier, it is now lower. The point is, can we attribute it to the hospital being built? Can we or can we not?
We need to have another group with which we compare it.
So basically the problem with saying that lower maternal mortality in Nandurbar post building the hospital is a result of the hospital The problem there is that maternal mortality is declining across the country. Right? Okay? So, if you had another region where the hospital was not built and you had a decline in maternal mortality, right? We would expect maternal mortality to decline faster in places where you built a hospital compared to where you did not build a hospital. Right? So what you're doing is you are saying that the difference in maternal mortality between pre and post hospital. So suppose the hospital was built in say 2015, right? You had data for 2010 for Nandurbar where you built a hospital, data for 2010 in another district which was far off, people couldn't travel, but otherwise similar, where there was no hospital. From 2010, you built a hospital in 2015. Suppose the maternal mortality there was, say, 90 women per 10,000 births. And here it was, say, 70 women for 10,000 births. So where you built the hospital, it was 90 women. And that's why you thought that you need to build a hospital. The other place where you didn't build the hospital, it was 70 women without, per 70 deaths per 10,000 births. Then you built a hospital in 2015. 2020, again you measured maternal mortality. So if it was 90, it became 30. When it was 70, it became 50. Right? So where it was, you did not build a hospital, it fell from 70 to 50, 20 points. Where you built a hospital, it fell from 90 to 30. So the difference among differences, the difference in maternal mortality, if you compare the difference in maternal mortality where you did not build a hospital and the difference in maternal mortality where you built the hospital, the difference in maternal mortality is higher where you build the hospital compared to maternal mortality to the difference where you did not build a hospital, right? Then you would say that this is because of the hospital. Okay? Assuming, of course, that things would have gone in the same direction otherwise, right? Okay? So therefore, it's a difference in difference method. You see why it's called a difference in difference method now. Okay, and that really is a very good application of dummy variables. So let me quickly take you that. So let's not forget all this, right? So basically, so this you can read. It is free to read. So I'm going to take you through that. This all just explains what I said. Okay. So you basically run a model like this, right? So there are two groups. One is a group which is treated and the other group is a control group. So you built a hospital in Nandurbar, so population in Nandurbar would be treated population. You did not build a hospital in Dhule, so the population in Dhule would be the control population. Right? Okay. Right. Secondly, what you have is the treatment. Right? So there are two dummies. One dummy which describes whether a group is a treated group or a control group. And the other describes the time period, the treatment time period, right? Okay? After the treatment, before the treatment. Right? So this is treated group. Right? This is after treatment. So the dummy is 1 for all time period after treatment, 0 before treatment. Right? So you got two dummies. One dummy which is 1 for treated groups, irrespective of before and after treatment. And 0 for the control groups, irrespective of before or after treatment. Right? And then there is another group, another dummy, which is 1 for both the groups for time periods after treatment. And 0 for both the groups before treatment. Right? Sure? Okay. Now, see what happens. Look at the treated group after treatment, right? This is what? Beta 0 plus beta 1 treated group plus beta 2 after treatment plus beta 3 treated group into after treatment, right? So, for Nandurbar before treatment, right? What would this be? Nandurbar is the treated group, right? Nandurbar is the treated group, right? Before treatment, the after treatment dummy is 0, right? So it would be 1 here, right? And this part will be 0, right? So for Nandurbar, before treatment, your model will be beta 0 plus beta 1. Write this down. Right? For Nandurbar before treatment, your model will be beta 0 plus beta 1. Okay? For Nandurbar after treatment, what would this model be?
Beta naught plus beta 1 plus beta 2 plus beta 3.
Plus beta 3. Right? For Nandurbar after treatment, because this will be 1, this will be 1, it will be beta 0 plus beta 1 plus beta 2 plus beta 3. Right? Sure? So what is Nandurbar before treatment? Beta 0 plus beta 1. What is Nandurbar after treatment? Beta 2 plus beta 3 plus beta 0 plus beta 1. So what is the difference in Nandurbar before and after treatment? Beta 2 plus beta 3. Now come to Dhule. What would be Dhule before treatment? Beta 0. Right? Dhule will be beta naught. Right? What would be Dhule after treatment? Beta naught plus beta 2. Right? So Dhule after treatment. So what is the difference in Dhule? Beta 2 will be the difference in Dhule. What is the difference in Nandurbar? Beta 2 plus beta 3. So what is the difference in differences? Beta 3. So if you find the coefficient of beta 3 to be significant and negative, you would say that the treatment has worked. This is the treatment. This is called the difference in difference estimator. But there is an assumption. The assumption is that suppose something else had happened in Dhule, right, in Nandurbar. Suppose suddenly some NGO has started to come and educate people about good health and all those kinds of things, or do something, which meant that the decline. So basically, if before the NGO coming in, if the maternal mortality was dropping in Dhule, in Nandurbar like this, because now some other NGO has come in, it has started to drop. Right? Okay. Then our model will not be valid. So the assumption is that the decline in the trend in Dhule and trend in Nandurbar should have gone in the same, it would have continued the way they were, right? Except for the treatment. You get the point? This is called the assumption of parallel trends. So what you are saying is that this would have been Dhule, this would have been Nandurbar, right? And after the treatment, the Nandurbar trend shifted down. Had there been no intervention, the Nandurbar trend would have continued like this. So if you actually find beta 3 to be 0, you would expect that the Nandurbar trend would have continued to be like this. So what you are really asking the question is, if beta 3 is 0, we are really asking a counterfactual question. What would have been the trend in Nandurbar had there been no intervention? Right? In which case the mean values, so basically in which case, we are asking, if is that trend shifted, beta 3 will be the coefficient for that. Right? This is the broad idea behind the treatment, the difference in difference estimators. Everybody gets this? Sure? Pakka? Yes, it's a very important technique used in policy evaluation, right? So basically, you can actually run this now. Okay, there's an R code, Python code, Stata code, everything. A wonderful book, right? And it's free. So if you get these libraries, these libraries, and we're looking at an organ donation program, right? Does an organ donation program reduce whatever, right? So what is that organ donation program? So what is the organ donation study? The organ donation study, you will find it here. Let me find out what the organ donation study here is.
Is it the default option? Yes or no? ये organ donate करते का
नहीं करायचं.
जो असे
Okay.
that behavioral.
Yeah, but how have they used it? It's because they are doing some policy evaluation there, no?
Organ donation increases if you change the default. So sir, difference in differences, what is used in randomized control trials?
No, randomized control trials don't need a difference in difference. Because,
Same study, but they are written instead of active choice phrasing or organ donation rates. So when they change the form from the initial form, the default setting is that they have to select if they want to donate the organs.
okay. So what they're saying is if you change the form, is there more organ donation?
If you don't want to donate, then you have to select. That is
Okay.
the new form. So when they give the new form, does that increase the
Organ donation rate. And some people changed, some people did not change it. No, for a RCT you don't have to.
No, the thing is that it's a behavioral thing that by default, whatever is there, you tend to go with it. You don't,
Okay.
actually go and
Right.
choose the thing. So when they make that the default setting, then I will donate my organ.
So that's how they're trying to evaluate that policy.
So after that, the organ donation rates increase.
Yeah, but we need to run the econometric model. Yeah. No, for an RCT, see, essentially the problem with policy evaluation is, for example, it might be the case that a hospital got opened in, in Nandurbar for some, there was an NGO actively working there or whatever, right? So there could actually be endogeneity there, right? So whereas, and therefore you need to do this randomized control trial. So there are many factors which are anyway driving mortality. Now you see there is an additional thing. For an RCT, you don't have a pre-post, right, in that sense. Right, for RCT what you have a treatment group, you have a control group. And because you have randomized the treatment groups, right, you are sure that there are no confounding correlates which are determining who the participants in the treatment group are. Right? And therefore, all that you need to do is a hypothesis test between the two means. Right? The idea of an RCT is to remove the confounders by selection. Like for instance, if I say that Pune University started a gym and after 1 year, I check the BMIs of students who go to the gym and those who do not go to the gym. And I think that the students who go to the gym are healthier than students who don't go to the gym. That does not mean that the gym has created this difference. It could be that students who were anyway doing other things or eating well, etc., they were health conscious. So they said, let me go to the gym. And the couch potato said, to hell with the gym, I'm not going to go there. Right? So the results could actually be the function of the student categories. But when I randomize that, so what I do is actually, I set up a gym, I do a pre-comparison of students who are, so I randomize selection. So I kind of randomly select 500 students who can now access the gym, right? So that their attitudes don't need to bother, because it's not a selection of really the active guys, health conscious guys who are going to the gym and lazy guys who are sleeping out there. But now we have randomized them. So it's enough to actually just compare the two means, no? Because this part has gone away. The confounding effects are no longer there.
And there's no randomization
In fact, randomization is generally not possible in many cases. how do you react if only some students in your university got a pass to use the gym and you didn't get to use the gym for 1 year? You get very angry, no? Yeah, they did this experiment somewhere in Kenya where actually a very large number of poor people were deliberately deprived of water, electricity, etc. They want to randomize this, right? So randomize is not always possible. Yeah, so therefore you need to have.
It is done on like the major studies are being done.
Yeah, I know, but they are a little. See, it becomes a problem. For instance, we only get successful studies which are reported to you, right? But for policy purpose, it becomes very hard to really see and there are only many sub questions which don't get answered. For example, if I decide to give, say, additional rations, say 1 kilo of rice to every woman who brings her child I want to see whether giving 1 kilo of additional rations to people who bring their children to Anganwadis, will it improve, will it increase attendance, right? So what I do is I kind of randomize this for some reason, right? For some people who are coming to the Anganwadis, they get a packet of rice, and some people who are coming to the Anganwadis don't get a packet of rice, right? And I kind of explain and things like that, right? But then, when I actually want to translate to policy, then the immediate question is, okay, when we did this experiment, we got some 100 quintals of rice. But as a state, I had to buy 500 tons of rice. So there's a procurement process that I should do. So I get it through a tender, right? And then I see that the quality of rice which I gave was not as good as the quality of rice which I gave in the experiment, right? So it doesn't matter. So then the original experiment should actually have also factored in quality, right? So you get a lot of post problems like this, right? And so any good policymaker will tell you that this really doesn't work so quantitatively, right? You have to have a good sense of the ground. You have to go to the understanding of people, what will work, how do people. Policymaking is a very, very complex process, right? It really can't really be resolved only by saying that, some kind of a statistical measure is good, but it's often hard to design it properly. And so therefore it always has to be a lot of qualitative understanding with appropriate methods and numbers thrown in. Yeah. So for instance, any evaluation of Forest Rights Act, for example, statistically is very difficult. He knows that, right? And there are many spin-offs. Many times things happen which you couldn't have anticipated earlier. Right? For example, my friend who is a very senior journalist in central India, he interviewed some very senior Nakshal leaders who had surrendered. And some told him that what hit them most was not the police or the Forest Rights Act, because people now got an alternate political program and they were now handing their future in their own hands. So they said, we don't need you guys, go away, right? Okay, so it's many spin-offs. It's not, and policies are so open-ended, they do so many different things. Right? What you anticipate in one way doesn't always happen in another way. Policies are highly open-ended. Many different impacts which you could not have. So basically you do good things, you do bad things. That's all.
So there was this iron deficiency program.
Right.
So they gave iron tablets to women, pregnant women. And afterwards they went to see what happened. So the women did not eat those tablets. They gave it to the cattle. They thought they will give more milk. And they were afraid that if the baby's size increases, it will be difficult for them. So they were not eating the tablets.
Yeah. No, it's a very policy is very complex, right? You just can't solve it by one statistical method. You have to have a very good understanding of the ground, people who you're working with. Yeah, like for example, I'll digress 2 minutes, but so there is a very interesting exercise in Pune that happened at the beginning of the 19th century. Right, when this area in Pune was conquered by the British, they wanted to understand how to tax agriculture. Because this Maratha regime, they are very politically negotiated land revenue arrangements, right? So if you were powerful enough and you said you could defer, so you did not pay taxes. Right? There was some land which nobody cultivated, then there were again tax concessions. Right? But these guys wanted to have a system. So very early on, there was all the East India Company officers used to learn, we were taught at those who were educated, not everybody was educated, but the educated officers were taught at a college called Haileybury, where Malthus used to teach. Right, and Malthus used to teach them Ricardo theory, right? So there was this officer called Mr. Pringle who came to Pune and said, why are you guys worried about all this? Right, we have learned from Mr. Ricardo that there is called rent, no, net produce. So if you take the output of a farm and subtract from it all the cost of production, that is supposed to be rent, right? And all that we'll do is we'll calculate the rent on every farm, and the state will take half of it, farmers will keep half of it. So farmers will also have to have profit, state will also have a profit, and agriculture will prosper, and because farming is profitable, markets will develop, and land will develop, and this will become definitely more market-driven kind of agriculture. So the officers of the East India Company at that time were basically soldiers, right? They said that, okay, we'll give you do this in 100 villages, 80 villages in Indapur. So he went and did some very detailed calculation to every farm. Measure the farm, included all the costs of production, so much so that if you had cattle, the insurance on that cattle, etc., etc. So every farm, he had a detailed estimate of what the net produce of that farm was. And then he said, okay, now we take 50%. The only thing which the British government told him was that whatever you do, our revenue should not fall. Just like GST, this has to be revenue neutral. So for every village, right, our total collections from that village should not fall. You do whatever you want, right? So Mr. Pringle thought, okay, that's a constraint I have to work with. And so for each village, he kept the total number constant, but redistributed all the land burdens, right? So where there was more profit, he would take more. Where there was less profit, he would take less, and so on. And as a result, what happened? What he thought exactly opposite. People simply ran away from those villages. And those who stayed back had to be put in jail. They could just not pay that money. Right? So why did that happen? So when we looked in detail at the data, we realized that actually it was not as simple as it looked like. Right? People in Maharashtra, in that area already did not have, when Mr. Pringle took over, unlike what Mr. Pringle thought that land can be measured with some meter unit, etc., there were actually several different measures of land. Right? One was called a Rivaj Biga, which was a customary Biga measure, which was very flexible. Right? Because land tax under the Peshwas was on a per acre basis. So if you're a rich fellow, then the Rivaj Biga on your farm was also big. So your land, if it was 100 acres, was shown to be only 70 acres. Right? If you're not very politically powerful, then of course the Rivaj Biga was what it was. So the rich people were evading taxes under the Peshwa rule. And when Mr. Pringle's men went with all those measures, the rich folks realized that they were going to lose. So they bribed these guys. They said, okay, let our land be what it is, you don't please. So the burden on them fell, but the total burden had to be the same. So it all increased on the poor people who were already very poor. And so that whole exercise had to be given up. Right? So many times policy is not what policy, policy works with an existing structure. I think they agreed with what is right? Okay. So you have to be careful, right? Okay, so let's do this regression now. So thankfully we understood what needs to be done, no? Right, so let's run this. Okay. So we have this now. You have to install these libraries. Should I make this a little bigger? अरे यार ये गड़बड़ हो जाता है. Yeah. Yeah, here. एथिकल इश्यूज पण होते. हो ते
ड्रग टेस्ट
हो हो एक्झॅक्टली. Yeah. There are many ethical issues in. And they're so expensive to carry out.
ड्रग टेस्ट मध्ये तर they do that all the time.
So if you run this, you get the so California was treated in these 3 quarters, right? M summary is model summary. And stars are the levels of significance. So क्या आ रहा है? So आ गया? क्या आया? What is the treatment coefficient? Are you getting this? Minus 0.022. So it means that active selection led to a reduction of organ donation rates by minus 0.022 in states where active selection was allowed compared to states where it was not allowed. So organ donation rates were declining anyway, but in states where it was allowed, a voluntary choice was allowed, the decline was minus 0.022% more, right, than the states where there was no active selection, right, where people were automatically enrolled. Yeah? Right? This is not the full treatment of the subject, but you can read this. Okay, what is a parallel trend assumption and so on can be read, right?
So, there are two other parameters. One is AIC and one is BIC. What does that mean? It's
The-
not there in the textbook, but it's shown
Yeah.
around.
Yeah, the Ekaiki information criteria, they are something like the R square, right? But lower the AIC, the better is the chosen model, right? It's Bayesian information base criterion and the Ekaiki information criterion. So it's like the adjusted R square really, but obverse of that. Okay, now there is another method called regression discontinuity design. Right? What's a regression discontinuity design? So suppose in the 9th standard you gave a scholarship to all students who have got more than 75% of the marks. Right? Okay? And then they sat for the 10th standard exam. And then you get your 10th standard results. You want to check whether students who you gave scholarship to have done better in the 10th standard exams compared to students who did not give the scholarship to. But just comparing the marks of students in the 10th standard exam of those who have got the scholarship and those who have not got the scholarship is not the correct thing. Because 9th standard you gave scholarship to students who are getting more marks. So probably you had chosen the more harder working and brighter students anyway, right? And therefore the difference in the 10th standard marks is not the difference in your scholarship, but the difference in students who have, in their abilities, right? So how do you answer this question? So you say that, okay, if you keep marks on the y-axis in the 10th standard, right, and the marks on the x-axis, on the 9th standard on the x-axis, right, so marks on the 10th standard on the y-axis, marks on the 9th standard in the x-axis, then you should get a positive relationship. More marks in the 9th standard, more marks in the 10th standard. You introduce a scholarship at 75%. Right? So if this relationship was like this, and if you're, so you should get something like this. Okay? So you should get something like this picture here. Yeah? So if this was, so this was how marks were increasing. If this is 9th standard marks and 10th standard marks were increasing, and if you had not given the scholarship, they would have increased like this. But you've given a scholarship, so they are higher now. Right? So you want to see whether there is this jump. Right? Okay, had there been no jump, had scholarship made no impact, then this would have gone on like this. Right? But you expect that those who got the scholarship, so this was the 75% cutoff, all those here are treated, all those here are untreated. And if you expect the treated group to have had a higher trend compared to the non-treated group, there should be a jump. How do you test this jump? Then you argue that, okay, take a student who has got 75.01% marks. She got the scholarship. Take a student who has got 74.9 marks. He did not get the scholarship. The difference in marks is very small. So probably there are students with just the same ability. Right? But one of them is treated, one of them is not treated. So now you're solving the ability question by working just around the cutoff. Right? So you look at the whether there is a significant change in the marks around the cutoff. Right? So you take a bandwidth around the cutoff. You take a small circle around the cutoff, which is called a neighborhood or a bandwidth or whatever. And within that bandwidth, whether, for example, 74.5, 74 to 75%, you think there is no difference. 75 to 76% marks, there is no difference. Right? And then you take only students who got 74 to 75% marks and students who got 75 to 76% marks, and you compare the means. Right? Okay, how do you do that? But you might have too few data points. So what you do that is, you set up a variable like this. You set up a regression like this. Where the 9th standard marks are the running variable. Right? Y is the marks in the 10th standard. The running variable are marks in the 9th standard. The cutoff is 75% marks. Right? Okay. T is the treatment, is a student who's got a scholarship will be 1, otherwise 0. Right? Okay? Sure? Now, add the cutoff, what will this regression be? You are assuming that students who got 75% have got the scholarship, right? If you got less than 75, you don't get a scholarship. 75% is the cutoff. So for students who have got exactly 75%, this will be 0, right? This will be 1, right? This will be 0 again. Yeah? So the model for students who have got 75% right? Okay, who got exactly 75% is beta 0 plus beta 2. Okay? For everybody else, it is beta 0 plus beta 1 plus beta 2, beta 3 into treated x. So, for example, students have been treated, right? Students have got the treatment, who have got the scholarship. Otherwise, what is the model? Beta 0 plus beta 2 plus beta 1 plus beta 3, right? So, because this and this will be the same variable, correct? Because treated will be 1. Yeah? So it is beta 0 plus beta 1 running cutoff plus beta 2 into treated plus beta 3, etc. Right? Okay. And for students who have not got the scholarship, it will simply be beta 0 plus beta 1 into running minus cutoff. Correct? So basically, yeah.
So in that case, when you're talking about students below 75, will beta 1 have negative?
Beta 1 will be, all these coefficients will be, all these values will be negative, no? This will all be negative, right? So running minus cutoff will all be negative. For students who got above 75%, this will all be positive, right? Okay, so what is a running variable which is centered around the cutoff by using running minus cutoff. Takes a negative value to the left of the cutoff, positive value to the right of the cutoff, right? So we are looking at a sharp discontinuity at the cutoff. A variable which takes negative values at the cutoff, positive values beyond the cutoff, right? Okay, sure? Okay. So basically you're looking at something like this. Yeah? So beta 2 basically, right, so our estimate of how big the jump is from one line to the other at the cutoff is simply the change in the intercepts, which is beta 0 plus beta 2 minus beta 0, which is simply beta 2. So the coefficient here, this coefficient really gives you whether the treatment has worked or not. Right? Sure? That's a simple regression discontinuity design. So we learnt of two ways of policy evaluation, the regression discontinuity design and difference and difference, both of which rely on dummy variable models. Right? I encourage you to read this chapter a little bit more carefully. Yeah? This cause and that chapter, both of them are freely available. Data are there. Run those regressions. They are very important policy evaluation tools. Difference and regression discontinuity designs. Alright? So at the cutoff, those who have not been treated, look at it again. At the cutoff, those who have not been treated will be simply beta 0. At the cutoff, those who have been treated will be beta 0 plus beta 2. So if there is a difference at the cutoff, that is beta 2. Very elegant, no? So all that you require to see is student's marks, cutoff, put it into this regression, whether student got a scholarship or not, and run this regression. And see whether this coefficient is statistically significant. So just go to the 10th standard, get all the marks of students, ask whether they ask them to fill up a form, right? What is your 9th standard marks? Whether you got a scholarship, right? Why with the 10th standard marks? Running minus cutoff. So whatever marks they have got minus their 9th standard, their 75%, and whether they got a scholarship or not. And if B2 is significant, then you say that scholarship worked, or otherwise it didn't work. You can do it also in geography. So for example, you are really interested in whether there is a, say, the same funding for schools, right, translates into lower attendance in Vidarbha compared to, say, then all that you have to do is to take the geographical gap boundary between Vidarbha and do this for geographical boundaries. That's all. Right? Okay? So look at this book, The Effect. It's a very well written book, very simple. The R code is earlier given. You'll be able to really learn about many policy evaluation concepts from this. Yeah? Next lecture will be our last class. Right? We'll wind up. And what did you guys send anything to Savita on the homework that I've given you? Just send it, no? So that we'll be able to actually also look at whether you really understood what you've done so far. Right? Yeah? It's not a test or anything. It's just a way to look at it, and if there is something that needs to be improved, then just a way of... There is no judgment involved in this, okay? And you can redo it again. If you want, you can send it to me anonymously through another email, which I can respond. If you don't want to, you're feeling embarrassed, right? Okay. So thank you, folks. Thank you so much.
Interrupted time series RDD only, but based on time.
Which one?
Interrupted time.
Yeah. Already only waste on time. Okay. Thank you, folks. This book, there's a book by Fansworth on econometrics, 2008, which we'll send to you. It's a free PDF. And those two books which I said are very good. Next class we'll talk about instrumental variables, because they're also another way of dealing with endogeneity and all that. And then we'll have a chutti. Yeah? Okay, thank you, folks.